Let us take a look at a practice problem over here, and I'm going to break it into smaller chunks for you, step by step, to help you understand what we're trying to do over here and how we can apply KCL. Some students believe that KCL is a good technique only for scenarios where you have current sources. Not true. Current sources do make it a little bit easier because then you don't have to write equations for the current in a, for example, let's say if I didn't have a 9-volt source over here, I had a 9 amp current source rather than a voltage source. The way it becomes easier is that now I directly know the amount of current that is flowing through this branch, right? And you're going to see that we have to write equations using Ohm's law for the branch currents, right? So that's what it makes it, that's what makes the current sources easy. But this concept that KCL applies when there are more current sources as compared to voltage sources, this is not 100% accurate, okay? So what we're going to do is in a systematic manner, tackle this problem, tackle this particular circuit. And in general, circuit analysis basically means that you're trying to figure out all the unknown currents in different branches and all the unknown voltages at different nodes in a circuit. Okay, the current is pretty obvious. It's easy to understand. Current through the 2K is unknown current in this branch. Current through this 2K is unknown current in this branch. Current through this 2K is unknown current in that branch, and so on and so forth. The concept of node is a little bit tricky one. Okay, and this systematic approach where you are asking yourself the questions and asking yourself the right questions will help you solve the problem. The first question that you need to ask yourself is which of these points in the circuit qualify as nodes? Okay. And in other words, what is the definition of a node? So this is a node. This is a node. Is this a node? Is this a node? It depends. It depends on what exists between all of these points. So the reason that this is a unique node with respect to this one, like they're not two same points, it's obvious because there is a resistor in between. But if I look at this point and if I compare it with this point, you may say, Wasim, this is actually a node. And some of you may say that this is actually not a node. Well, the fact of the matter is that this is a node, but both are same points. And the reason is that in between them, there is no circuit element. And this circuit element does not need to be a resistor, doesn't need to be a capacitor, doesn't need to be an inductor. It can be either one of those, or it can be a current source, a dependent current source, an independent current source. It can be a voltage source, dependent voltage source, independent voltage source. So if you see any box in between them, then the voltage at this point and the voltage at this point is not necessarily the same. So they become two independent nodes. Okay, this is an important concept to understand. And for that same reason, this red dot over here is a node with respect to this one because there is a circuit element in between it, right? And this particular blue dot is a node with respect to this blue dot because there is a circuit element in between them. But when I look at this blue dot, and this blue dot, all of them are actually a single node because there is no circuit element between any one of these. They are essentially shorts. They are the same potential, same voltage. Okay. So it's very important to understand what qualifies as a node in a circuit. Now, the second point that is connected to this first one is the concept of virtual ground. In some circuits, when you analyze them, you actually have, one branch, two branch, three branch, components here, components here, components here, components here, and you may explicitly be given a ground. Okay. The fact of the matter is that ground is nothing but a common reference point. Okay. The same potential reference that can be used. And if you are not given a ground explicitly, you can still add a virtual ground. Okay. This is important. It makes our calculations easier. So in the given circuit, I actually don't have a ground, but I can throw a virtual ground over here with respect to which I'm going to calculate other voltages. So it's a common node, a common reference point, which we can consider as a ground. Okay. Where should I write the KCL equations? This is a third question. You should write the KCL equations at the nodes. Okay. Or more specifically at the nodes where you do not know the voltage. It's important. Let me explain you why. So if I look at this circuit, right, that we're discussing, and let me simplify it by adding a virtual ground over here. So is there a need to write a KCL over here, a KCL over here, a KCL over here, a KCL over here at all of these 4 blue dots? Well, the first answer is that all of them are the same node, are the same point. So even if you want to write an equation, that equation should just be written for one of these nodes. And since they're the same voltages, you're done with that. Makes sense? Because it's a common reference point. And then the next question is that, is it an unknown voltage, right? Because KCL should be written at nodes where the voltages are unknown. Okay, let me write this here. KCL is written at unknown, at nodes with unknown voltages. Okay. So this common reference is a node, we all agree. But do we know the voltage here? Yes, it's a virtual ground. So this is 0 volts. So there's not much value in writing a KCL over here. Okay. What about this guy? This is a node because between these two, there is a circuit element. And this is a node between these two, there's a circuit element. And this is not a node, it's the same point. So we're going to ignore that. Now we have 3 candidates. I'm going to write 1, 2, and 3. Let's start with number 1. Should I write a KCL at number 1? Well, let's see. There is a 9-volt battery source over here, right? Which basically means that this is the positive terminal and this is the negative terminal of this 9-volt battery source. So if I write this, so V 9 volts is equal to the voltage difference between V1, which is this one, or I should say the voltage difference between V positive of the 9 volt and the V negative of the 9 volt. I'm taking baby steps over here, very granular, first principles, because until and unless you approach circuit analysis, at least during your first phase of learning, initial phase of learning, by means of these baby steps, it is very easy to confuse things, right? So all I'm saying over here is that the 9-volt battery, the voltage across it is simply the difference between its positive terminal and its negative terminal. No rocket science over here. And the positive terminal is connected to V1. So let us write this as V1 minus the negative terminal is connected to the 0 volt, right? Remember, we are trying to figure out whether a KCL is worth writing at this node or not. And the condition is that it should be the unknown voltage. Okay. Now, the 9-volt battery has 9 volts across it. So no issues writing that here. So it basically means that this voltage V1, right, is simply equal to 9 volt. We've been able to lock it. And as you do more and more practice with circuit analysis, you're going to get better and better at writing these equations because you can just eyeball it and see visually right away that the negative terminal is actually connected to 0 volts, right? So the positive terminal has to be 9 volt. Otherwise, you can actually take the systematic approach. So coming back to our question, do we need to write a nodal equation over here? And the answer is no, we don't, because I already know that this point is 9 volts. So what it leaves me with are these 2 points, these 2 nodes, right? And just by looking at it, just by eyeballing it, without doing any calculation or analysis, I cannot tell you what the voltage at point 2 is. I cannot tell you what the voltage at point 3 is, which basically means that I need to do a KCL. I need to write equations over there. Okay. And the fourth step, probably the most confusing step over here, is what directions should I assume for the current? Now, the answer to this question is that as part of your assumption phase of circuit analysis, there is no right or wrong assumption. I am going to repeat this one more time. There is no right or wrong assumption while you're doing KCL during that assumption phase. I can assume, for example, the current to be entering point 2 from the 9-volt battery, or I can assume it to be entering the 9-volt battery from point 2. Both are fine as long as my equations are consistent with my assumptions. In fact, the way that I am going to solve this circuit as a homework assignment, I invite you, I recommend you to actually flip all the current directions, solve the circuit yourself, and you are going to see that you still get the right answers. Maybe in some cases, you will have a negative sign associated with the current, which basically means that you simply have to do one step adjustment. The negative sign indicates that the actual direction of current is opposite. So don't stress, okay? Don't overcomplicate this particular step that I have to get my assumptions correct. Otherwise, it will be a wrong answer. That's not true, okay? There are certain guidelines, some tips, some rules of thumbs that I can provide you that will probably reduce the chances of you requiring an adjustment at the end. For example, if you have a 9-volt battery and this is the only battery and you have basically connected and shorted the negative terminal, this is a positive terminal, most likely the current will be leaving the positive terminal of the battery, right? Even if you have two batteries connected with the help of a resistor, the batteries are going to try and pump the current out. So I intentionally drew this battery a little bit bigger as compared to this one. Let's say this is 10 volts and let's say this is 8 volts. Both of them are going to try and pump the current out of their positive terminals, but it's just that the 10-volt battery is much larger than the 8-volt battery. So the net effect of the current will be from 10 volts to 8 volts. Okay, so if you see a battery like this, it's generally speaking a decent assumption that the current will be leaving the positive terminal of the battery. And what that leaves us with is that most likely the current is actually entering, okay, the terminal 2 from the 9-volt battery. I like to think of ground in terms of gravity, right? This is your common reference point. Everything that we throw up basically comes down. And visually as well, when you're looking at the circuits, it makes a little bit sense that the way that they're arranged, right? This node over here, this node over here, 2 and 3, current is falling from top to bottom, right? And it gives you a little bit of framework to sort of set the current directions. So I would assume that the current is falling down, the current is falling down. So I've now assumed the direction of current through this 6K. I've assumed the direction of current through this 2K. I've assumed the direction of current from for this 2K, right? So as you can see, both of these currents are leaving. So there must be a current that is entering. And you can reverse. In fact, I suggest as a homework assignment to reverse all of these current directions and then solve this circuit. You'll still get the right answer. You may need to do an adjustment at the end when you get negative values for the current. That's it. So there's nothing right or wrong during the assumption phase. What is important is your equations should be talking to your assumptions. And that's what we're going to ensure in the next steps. So you can see that there is a little bit of a groundwork with very subtle layers of understanding that we need to make use of in order to set the stage for KCL. There's no rocket science here. It's just that you need to have clarity on those small building blocks. And once you have multiple equations with multiple unknowns, you can use your Casio or TI-36 to solve for the unknown variables, and you can get the answer. The math is the easy part of circuit analysis, and sometimes students just get a little bit too distracted by using the calculators and not paying that much attention to investing their time and effort in understanding the concepts, okay? So what we are going to do over here is write equations using Ohm's law. So remember I told you that KCL actually builds on top of law of conservation of charge, and Ohm's law. For every single branch, when we write the equation of the current entering or the current leaving, we are going to use Ohm's law. And what is Ohm's law? V is equal to IR. We only have resistors over here, so that's fine. The one modification that I'm going to make over here to Ohm's law is that I'm going to say that delta V is equal to IR, which basically means that the drop in the voltage or the change in the voltage is equal to the current passing through the resistor. That's fine either way. And then I is equal to delta V divided by R. So if you keep this equation in front of you, you're going to see that figuring out the unknown currents in every single branch is actually very, very simple. Okay. So we are going to title this as VA, unknown voltage VA, unknown voltage VB. You can call it X, Y, you can call it alpha, beta, you can call it John and Bob, really doesn't matter. Okay. And a virtual ground over here. So the direction of I naught is already shown. Remember our directions. This was the direction we assumed, 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 and this is the direction we are working with. So when I write the equation for I naught, it is pretty simple. What is the delta V across this resistor? Because the current is going through this resistor, right? Entering from the top and leaving from the bottom. I have the positive sign over here because the terminal through which the current enters a resistor is considered positive. I have a negative sign over here because the terminal through which the current leaves a resistor is the negative terminal. And this also helps you remember that this is a V positive with respect to the resistor and this is the V negative. In other words, this is a higher voltage and this is a lower voltage, which basically means that when I'm writing the equation I naught is equal to delta V divided by 2K, right? Then in terms of the change in the voltage, which voltage is the higher voltage, right? Which voltage is the V positive and which voltage is the V negative? Okay. So the V positive is VB because the current always flows from the higher voltage to the lower voltage. What about V negative? 0 volt because this terminal is grounded. So I have one equation for I naught. And notice that underneath the KCL resides Ohm's law, right? Ohm's law is the most fundamental circuit analysis equation or rule or law, whatever you want to call it, principle that helps us analyze these circuits, right? So pretty simple, straightforward. So we have an equation for I naught in the form of VB. Can we stop here? Do we know everything that we need to know? The answer is not in terms of how many equations you've written. It is not even in terms of how much work you have done analyzing a circuit. You only need to ask yourself very simple question, one question. Do I have the same number of equations as the number of unknowns? When you have the same number of equations as the same number of unknowns, you can stop, you can pick up the calculator, use the method of matrices or linear systems, solve the linear equations, and you'll be done. If I ask that question, do I have the same number of equations as the number of unknowns at this stage? The answer is no. Why? I only have one equation. In terms of variables or unknowns, I have I naught, which is a variable unknown. I have VB, which is a variable unknown. So two unknowns, one equation. I need to write another equation. Make sense? This is the only question, only check that you have to do as you're solving the circuits. You don't need to mindlessly keep on writing an equation after an equation after an equation. Okay. So now at node A, what we are going to say is that we're going to write, what we're going to do is we're going to write the equation, right, for all the currents that are coming in. So we've assumed that this current is entering, this is leaving, and this is leaving. Pretty simple, straightforward. Always throw a virtual ground, right? Now using Ohm's law, assuming that this is the direction for the current flow from 9 volt to 1, the higher voltage is 9 volt, right? And remember that sum of current in has to be equal to sum of current out, correct? So the only current that is entering is from 9 volt to VA. So 9 volt is the higher voltage. VA must be the lower voltage because of this direction that we have assumed. It is not necessarily the right direction. We'll figure that out once we get the answers at the end, right? But this equation so far is consistent with the assumption divided by 3K. So this is a current that is entering, and this is simple Ohm's law, I is equal to delta V divided by R, or V plus minus V minus divided by R, okay? Or V high minus V low divided by R. It's the same thing, okay? And this is the current that is entering. And we are writing this equation at node A. What about the current that is leaving? Let's work with this branch first, right? So we have VA as a higher voltage. Remember, the terminal through which the current enters a resistor is a positive terminal. The terminal through which the current leaves is a negative terminal. And the 6K is a resistor. So with our assumption of the current actually entering from the top and leaving through the bottom and going to the ground, this basically takes the form of VA minus 0 divided by 6K. That is this current. Very easy, correct? Is there another current that is leaving VA? Yes, we have this guy over here, which is going from VA to VB, meaning VA is the higher one, higher voltage, and VB is the lower voltage, and 2K is the resistor. Make sense? Now, why did I collect these two currents on the right hand side? Why did I collect this current on the left hand side? Pretty simple. Collect all the currents that are entering on one side, collect all the currents that are leaving on the other side. You can switch that, right? You can have the current out on left, current in on right. But if you're not methodical with this, mistakes are made. Let's say if I ended up writing 9 volt minus VA divided by 3K plus VA minus VB divided by 2K on the left hand side, and I only had VA minus 0 divided by 6K on the right hand side, it would be inconsistent with my assumptions. Remember, it is not required, it's not mandatory, it's not a prerequisite that you hit the bullseye with your assumptions, that you don't have to make any adjustment at the end, right? The requirement is only that whatever you assume has to be consistent with your equations. Your equations should basically tell the picture that is in your assumptions on the circuit, and your circuit should paint the same picture that is painted by your equations. Okay. Another thing that we have to be mindful of is that when we start writing the equation at VB now, we should not all of a sudden make this current or any other current change direction. Once we have assumed the direction of current, right? For example, this is what our assumptions were. These are our assumptions from the get-go. They are frozen now throughout the circuit analysis until we get to the very final stage where we may have to make any adjustment. Make sense? So now as I move on to the next step, writing the equation at node B, I still have to carry this assumption. Okay, I cannot flip the direction of current between VA and VB. It still has to be the same. This is important, right? So now we are writing the equation at VB, pretty simple, straightforward. From the standpoint of VB, the current that is flowing from VA to VB through the 2K is actually entering, such that this is the positive, this is the negative. So VA is the higher one, VB is the lower one, the delta in the numerator divided by 2K. So this is in. And there are two currents that are out. The current through the 2K branch, this one, is VB minus 0 divided by 2K. The current through this one is also VB minus 0 divided by 2K. Now, when we look at the number of equations that we have, okay, and the number of unknowns. So if we just stopped at equation number 1, we had 2 unknowns, 1 equation. It didn't cut it for us, right? Then we wrote the equation at node A. We ended up with 1 more equation, right? And 1 more unknown. Okay, so we have at this stage, by the time we reach equation 1 to equation 2, we have 3 unknowns, and you should keep track of this, especially if this is your first time going through circuit analysis, or circuit analysis is not your strength, right? And you are in the phase of learning these processes in a systematic manner, techniques in a systematic manner. So far, after writing equation in 1 and 2, we have 3 unknowns and we have 2 equations. Then when I write equation number 3, it still has a variable in it, right? But it is the same variable. It contains the same 2 variables, VB and VA, which we have seen previously. So it did not introduce any new variable, right? So with the introduction of equation number 3, we still have 3 unknowns and we now have 3 equations. This has broken even, right? So with 3 equations, 3 unknown, you can plug it in the calculator, KCL or TI, and it will basically spit out the answers. The mathematics, the actual calculation portion is the easy stuff. And within my FE electrical and computer exam preparation program, within my PE power exam preparation program, I have tutorials, I have guidelines as to how to figure out the system of linear equations. So we have 3 linear equations and we have 3 unknowns. When we set up the equations properly in the calculator, tells us that my VA is equal to 3.6, my VB is equal to 1.2, and my I naught is equal to 0.6 milliamps. Now let's say hypothetically, after doing all of this, okay, we ended up with a voltage value of minus 3.6 and for VA and minus 1.2 for VB. The question is, do we need to do anything, any type of adjustment with VA and VB? Because we've ended up with negative signs. The answer is no. The negative signs that you arrive at, that you achieve for the voltages at the end does not require any adjustment. Okay? But hypothetically, let's say you ended up with minus 0.6 milliamps for the current. Now you need to do an adjustment, okay? Because a negative sign with the current, and it could have been because of the assumption that you made for any of the branch currents that basically resulted in a negative sign. What this means, please listen carefully, this is the final step basically, is that whatever you assumed in terms of the direction for this particular current, and if you go about calculating this current and if it ends up being negative, you don't do anything with the magnitude. The magnitude 0.6 milliamps is fine. There's no issue with that. The negative sign is saying that in reality, and this is hypothetical, the solution is not minus 0.6, it is 0.6 positive. But assuming that it was minus 0.6 milliamps, what it basically means is that you simply have to switch this. The current is actually flowing upwards. Okay, a current of 0.6 milliamps is actually flowing upwards rather than downwards. That's it. And if you end up with negative signs for voltages, you don't do anything. That is actually a negative voltage here, a negative voltage here, if that was the case. Exception handling is only done for the currents. So as you can see, KCL is no rocket science. It just requires you to carefully manage the circuit with the assumptions, with the equations, and do the proper analysis, use Ohm's law, be careful with the higher voltage, the lower voltage, the delta V, collect all the input currents on one side, the output currents, the outgoing currents on the other side, and then analyze it and solve it, right? But there are multiple tripwires throughout this, starting with passive sign convention, right? Being consistent with your assumptions and so on. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE power exam preparation programs, please visit my website, studyforfe.com.